Okay, it's a three-part question. So part A is find the slope of this curve at x equals -1. So let's worry about that first. We're going to need this information to carry on anyway. So to find the slope of a curve, hopefully at this point, you're just going to differentiate your function. My prime symbol was pretty wonky there. So f prime of x is differentiating both, I guess, all three of these pieces. So it's going to be minus times 3x squared. Bypass the 2 and multiply by the derivative of x squared, which is 2x. So 2 times 2x will be 4x. And then finally differentiating the constant 1 gives you 0. So here's our derivative. And if we want the slope of this curve at x equals -1, then of course we evaluate the derivative at -1. And this will give us 3 times a plus 1 once we square that negative 3 times a plus 1. I better write it down. We'll get -3 and then plus a -4 or subtract 4. So the slope of our curve is -7 at x equals -1. And to be clear, this is also our tangent slope. And that will help us a little bit later in this problem, particularly part C. So we got our slope of our curve at -1. So now let's consider part B. Part B is asking us to find all points of tangency where the slope of this curve is the same as the slope at x equals -1. So are there any more points on this cubic polynomial function that have the same slope as we found in part A, or -7? Well, that's a good question. But we got our derivative, so we can easily handle that. Part B is essentially just saying, can you find all x values that make your derivative equal to -7? So we want our slope of our curve to be -7. Now keep in mind, x equals -1 is one of those solutions, but of course we're looking for other solutions as well. So how do we do that? Well, you get rid of your f prime of x and you replace it with that quadratic expression. The derivative, of course, the expression for the derivative, minus 3x squared plus 4x. And you try to figure out how you can make that equal to -7. So I'm going to drag everything to one side here, relocate those left-hand terms, and our quadratic will become positive 3x squared minus 4x subtract 7. And I believe that's factorable. We'll find out in a few more seconds here. So let's use guess and check. Notice I'm not even bothered to check to see if it's factorable. Find out in a second if I don't have much success here. So that gives me 3x squared, and if I want to get a -7, then I gotta obviously put the couple of factors, the only two factors that'll multiply to give me -7 at the end. And this is a bad idea because that pairing will give me -21, which is not even close to -4. So let's back paddle here a little bit, and we'll put a +1 there and a -7 over here. So right away I'm guaranteed to get 3x squared and -7. Do I get -4? Of course, this is the check part of guess and check. And look at that. We get -7x plus 3, which is our middle coefficient. So we can go ahead now and solve this quadratic equation. And there's our new point of tangency, or the x location of the point of tangency, because guess what? If we solve x plus 1 equals 0, we get the x equals -1 value. And that's a good sign, because we knew the slope of our curve at that x value was -7. That's how we got this equation in the first place. So this is confirming that our answer is correct. So to solve 3x minus 7 equals 0, add 7 to both sides and divide by 3. I guess we'll go back to our original color here. So this will be x equals 7/3. Okay, so do we need x values or points? What do we need? Usually that should say find the coordinates of the points, but I think that was my laziness there in typing that in. All points of tangency. So let's list the ordered pairs, and then we realize that's going to be a real annoying when we have to put 7/3 into that function. So we don't know whether this is paper 1 or paper 2, and I guess I can make the call. Let's write down our points of tangency here using function notation. And of course, this wouldn't give us full marks on an IB assessment. But I think what we'll do is we'll get those 2 points of tangency on our TI Inspire, And I'll show you, you might already know how to do this, how to actually get those exact y values using your TI-Nspire. Now we can probably handle doing this, but again, just to speed things up and getting some more calculator chops is never a bad thing either. Okay, so here we are in the TI-Nspire. Let's add a graph first. It's probably the easiest way, and we'll get our points of tangency on here. And they will show up in decimal form as always, and then we'll show you how to get them converted into their exact values. So negative x cubed plus 2x squared, and the constant was plus 1. Here's our cubic polynomial function, and let's put on our 2 points of tangency by using the trace feature. I guess there's a couple of ways we can do this, but this is by far the easiest. So at x equals -1, type it in, hit enter, and 2 enters to make sure that point is stuck right on your curve. And the other x value was a little weirder, but that was 7/3, and that'll definitely show up as a decimal. And there it is. Hit escape. And we'll do some label moving here, not too much, so we can still see things. That y value, of course, it'd be nice to have the exact value of that. That is 7/3 in decimal form. So we'll worry about that maybe in 2 more seconds, since we're already in the graphing window here. Let's put our tangent lines on these 2 points to confirm that they both have a tangent slope of -7. So that, of course, is under your geometry feature, which, remember, if you're working with the scratch pad, you won't see this, so you got to open a document. So under points and lines, and we want a tangent line. We want one there, and we want one there. So we'll hit escape, do some label moving, and it looks like both of those tangent equations have the same x coefficient, and most importantly, the x coefficient is -7. So that confirms that our analytic work is 100% correct. And now let's see how we can get those. I guess we already know this is an exact ordered pair, -1 and 4. Let's see if we can get the exact set of coordinates for that second point of tangency before we worry about the rest of this problem. So I'm going to go back to home here and open up just a regular calculator. And since we already entered f1, our function into f of 1, we can just evaluate that function anywhere we want. And I guess we could put in -1 to return the y value of 4. But I think the one we really want to do, or at least I want to avoid doing, is going 7/3 and putting that into our cubic polynomial. Of course, we could do that if we really had to, but that tends to be a little bit more tedious than normal. If you had to do something like that, it's probably a paper 2 question anyway. So here are our 2 points of tangency as we now move back to our pencil and paper work and finish off part C. Okay, so thanks to the TI-Nspire, we can just, I guess, doctor this up a little bit. And get rid of the function notation and write those 2 exact ordered pairs. And this one was easy to remember. That was a +4. And this one was, what, a little harder to memorize, -22 over 27. Okay, so that's that. That saved us a few moments of tinkering around and evaluating that function, especially that x value of 7/3. So now we can finally get to the new item in this video. We have to find the exact equation of the normal line at both of those points of tangency. So as I said in the very earliest stages of this video, a normal line is a perpendicular line, or a line perpendicular to the tangent at these points of tangency. So we have to remember how we can find a perpendicular slope. So I'll keep those 2 points of tangency on the screen. Also remind you and myself that right now the slope of our tangent line for both of these ordered pairs was -7. Now if I wanted the equation of my tangent lines, of course I'd be using that slope. If you want the equation of your normal line, that's going to have a slope that's perpendicular to the slope of -7. And if you can remember how to do that, wonderful. It's actually not that difficult. You change the sign. So -7 becomes +7, and you also have to take the reciprocal of it. So usually what we say are if 2 slopes are negative reciprocals of each other, then those 2 slopes are perpendicular. A little mathier way of writing that relationship is usually by saying the product of the 2 slopes are -1 if the 2 slopes are perpendicular. And if you solve that product, I guess, for either one of those two slopes. How about subscript 2? Here's where our negative reciprocal comes from if you divide both sides of that equation by m1 or m2 for that matter. So that is one way of writing, probably the most common way of writing your relationship if you have two perpendicular slopes or lines. So we got our normal slope, we have our 2 points of tangency. Now we just have to go ahead and get those two exact, unfortunately exact equations of these normal lines. So let's do that. I think we'll be smart to start with our easier ordered pair, which I think I'll just label here. I'm going to work with x1 and y1 first, which is the negative 1 and 4 ordered pair. Probably should leave it on the screen. Why don't I get rid of this? We don't need this anymore. It's right smack in the way. We got what we needed from that. And you saw it. That's all that matters. So next thing you're going to see is our point-slope form of our equation. Since we have a slope and we have a point that we want for, I guess, both of these normal lines. So remember, this is a rearranged slope formula. And I'm going to rearrange it one step further by adding y1 to both sides. I find it less tedious and less sign changes, especially for that second ordered pair where your y value is negative. So that's the same relationship. It's just a little bit more convenient way of writing your point-slope form. So let's write our first normal line. Maybe we'll do this one in green, or we'll say this equation of this normal line using the ordered pair negative 1 and 4. We're going to use the slope of 1/7. And it's going to be x minus x1, which will be plus 1. And then we have to add on 4. So a little bit of work here. 1/7 x will expand this out. And then we'll have plus 1/7 plus 4. So of course that's 4 1/7, mixed fraction, if you're just adding that to the integer 4. So we could write that as a mixed fraction. And if you want to add both of those together, you could also write that as 28 plus 1 over 7, or 29 over 7, which I think I will. That's a little bit more common, but again, it really doesn't matter. 29 over 7, or whether you want to say 4 1/7, matters little. Both are 100% correct, and most importantly, those are exact numbers with no rounding. And I guess we're not using our calculator, at least at the moment. We will very shortly, to double check our work and show you that normal line feature on your TI Inspire. So we'll say this is normal equation number 1 at that order pair negative 1 and 4. So we have to repeat this process one more time, of course, using, I guess, orange, this one, x1 and y1. So let's go ahead and get some more space. And let's see if I can remember that point of tangency. Let's write out our slope, point-slope form, which is m times x minus x1. Remember, I'm just relocating my y subscript 1 to the right-hand side. It's easier to work with. And then in orange, same slope. This is still a normal line. And my point of tangency was at 7/3 as an x value. So I'm going to go minus 7/3. Then I'm going to add on my y value, which was negative 22 over 27. So of course that's just subtraction. Probably more coherent way of writing that. And then we have to expand this out and get our exact normal line. So we're going to get 1/7 x. And then we'll get 7 over 21 there, which of course is just a third after the subtraction. And then we have a little bit of fraction work to do, but nothing too serious because we let the TI Inspire do the hardest part for us to get that y value of negative 22 over 27. So we just got to get a common denominator here. We can handle that. Let's times top and bottom of that fraction by 9. And we'll have our exact normal equation, or I guess we should say the second exact normal equation, because we'll have minus 9 minus 22, which is negative 31 all over 27. So we'll box this somewhat straight. And then we'll go to our TI Inspire and we'll see how we can draw a perpendicular line at those points of tangencies. So we'll call this normal equation, our second one, normal EQ number 2. And we have our first one up here. We can barely get them on the window, but there they are. So it's a little bit tedious having to do both of them, but I guess the first time around, practicing to do it twice is not too big of a deal, I guess. Give you a little bit extra practice. And now to round out this video, let's see how we can plot those normal lines right on our TI Inspire, and maybe even find the equation as well, and then look at it in its exact form in our calculator window. Okay, so here we are back in our TI Inspire. Let's go to our graphing window. I think that's the best place to start, and let's see if we can maybe get some space, move those labels. We have our tangent equations there that we didn't really need other than confirm our tangent slopes were the same. So let's plot a perpendicular line at both of those points of tangency. So that's under Menu, under Geometry. That's where all the good stuff is, I think. And it's under Construction. You can see in that little graphic there, it looks like there was a, if I have to get out of here, looks like there's a pair of perpendicular lines at the little picture at the start of that construction menu. So hit that, and the very first thing is perpendicular. So if you want to hover over that, you have a little bit of flexibility here, I found. You can click the line and the point, or a point and the line. It seems to be able to do it. So if you can click on the point and then that line, you'll know if it works. If you see a line that looks like it's pretty perpendicular to that tangent line, which of course that is. There's no equation yet, but we'll fix that in a second. Let's put our other perpendicular line, aka normal line, on that second point of tangency. That was the fun one, remember, with the negative 22 over 27y value. So to get our equation to show up, I'm sure there's more than one way of doing this, but I find the control, the right click is the easiest way for me on the device or the computer. So if you go Control Menu, once you're hovering over that line and line shows up on your screen, that will give you a right click, and you want number 7. And that'll put your equation on there. Now it's in decimal form. But remember what we had 1/7 x, and that's 4 and a little bit, so that's our 4 and 1/7, or our 29/7 there, which we can check our decimal representations, I guess, in our calculator window here in a few more seconds. Same thing with this line. Hover over it, line pops up, go Control Menu, and that right clicks. Get that equation and definitely drag it so you can see it. And notice both of those equations have a positive coefficient, so those are the normal equations with the slightly positive slope. And there's our second y value that I forgot what we had, and I guess that was negative 31 over 27. So let's confirm some of those things and wrap up. Okay, so let's look at our slope. So I guess first things first. Now remember your calculator, at least mine is set to favor fractions. So if you punch in a fraction, I guess you could go Control Enter to switch it into a decimal. So if we go back to our window, our graphing window, you can see the 0.14. So of course that's corresponding to that 1/7. And the other thing I guess we found by hand was what, negative 31. Oops, I better use the negative symbol here. It doesn't know what you want. It was asking me if I wanted negative or subtraction. So let's go 31 divided by 27. And I'm just going to stick a decimal with that so it doesn't return a string character. It'll return the decimal representation, and that's negative 1.15. So again, back to our graphing window, and we can see negative 1.15. And I don't think we have to confirm that that's 4 and a 7th, because we know a 7th is 0.14 approximately. So we know our normal lines, equations of our normal lines are 100% correct, what we found in pencil and paper.